All right, welcome to this unit, Unit 5 on chemical bonding. In this unit, we're going to be talking about what it is that causes atoms to combine to form chemical bonds. Now, we know that there are about 115 elements on the periodic table, but there are literally millions of chemical compounds in our universe. Things like water, H2O, or CO2, carbon dioxide, or H2SO4, sulfuric acid. So what makes these atoms come together to form these compounds? Well, the answer is really pretty simple. Chemical bonds form because atoms are trying to feel as though they have an octet of 8 electrons around them. So 8 is the magic number. All atoms are trying to get to this number of 8 electrons in their outer shell. And the outer shell or valence electrons are the ones that are involved in chemical bonding. So let's look at a couple of examples. Let's start with sodium, for example. Sodium, we know, has 11 protons in its nucleus, and it has 11 electrons, of course, and those electrons are located as follows. 2 in the first main energy level, followed by another 8 in the next main energy level, and then one more in the last main energy level. So sodium is going to attempt to get rid of that last electron if it can get rid of it, because that would give it a total of 8 electrons in its outer shell. Now let's contrast that with fluorine. On the other side of the periodic table, fluorine has a total of 9 electrons. So let's place those electrons. So we're going to have 2 electrons here and then 7 more here. So that's a total of 9 electrons. So fluorine is going to try to find something that has one more electron so that it can have a total of 8 electrons in its outer shell. So that's how it works in our universe. Atoms are in a process of getting to that 8 valence electron number. The type of bonding then which occurs depends upon the difference in electronegativities between the atoms involved. Remember that electronegativity increases as you move from left to right, from left to right across the periodic table, and from bottom to top in a family or group. Fluorine has the highest electronegativity of all with a value of 4.0. So electronegativities, we won't worry about units, but I do want you to remember that fluorine in the upper right-hand corner is going to have an electronegativity of 4.0. So again, electronegativity increases as you move from lower left to upper right in the periodic table. Now, bonds between atoms. Bonds between metals and nonmetals generally are ionic bonds. Bonds between two nonmetals are covalent, and bonds between two metals are metallic. So we want to explore the various types of bonds now. First, we'll start with ionic bonds. Ionic bonds are chemical bonds that result from the electrical attraction between large numbers of cations and anions, and this is called ionic bonding. Now, in purely ionic bonding, atoms give up their electrons to other atoms. Let's take a look at an example. Here we have sodium. Sodium we've looked at, and it has 11 electrons, one of which is in the outermost energy level, the third main energy level. Chlorine, in its last main energy level, has 7 valence electrons. So what will happen is that sodium will give its electron to chlorine, allowing sodium to have 8 valence electrons in its outer shell, and chlorine to have 8 electrons in its outer shell. Both are happy. And when this happens many times, it forms what we call a crystal lattice. Think of a salt crystal. Sodium and chlorine coming together to form an ionic bond. But this happens not just once, but many times, where electrons are transferred from sodium onto chlorine, okay? Let's look at covalent bonding now. In covalent bonding, there's a sharing of electrons, okay? And by sharing, what we mean is that each electron is going to feel as though it has an octet of electrons. Let's take a look at the fluorine on the left-hand side. This fluorine has a total of 7 electrons. Let me circle those. 1, 2, 3, 4, 5, 6, and 7. And the other fluorine also feels as though it has 8 electrons. Let me circle those. Or 7 electrons, I should say. 1, 2, 3, 4, 5, 6, 7. But let's take a look at what's going to happen here. What's going to happen is that each atom is going to feel as though it has 8 electrons. Let's take a look at this atom first. 1, 2, 3, 4, 5, 6, 7, 8. This atom feels as though it has 1, 2, 3, 4, 5, 6, 7, 8. So both atoms benefit from this covalent bonding. Both atoms feel as though they have an octet of electrons. Now, if the electrons are shared equally, the covalent bond is known as nonpolar. There's not one side that's more dominant with electrons than the other. That's what we mean by nonpolar covalent. Now, ionically bonded atoms have a higher melting point than covalently bonded atoms because the atoms are much more tightly bonded together. In order for melting to occur, those bonds have to be broken. So for ionic bonding, it's higher. If the electrons are shared, but one atom is significantly more electronegative than the other, but not so significantly that the bond is ionic, then the bond is polar covalent. Let's take a look at a polar covalent bond. So here's the electron cloud for a polar covalent bond. Notice that the electrons are more densely populated around one atom than the other atom. So this is a covalent bond, but not a nonpolar covalent bond because there is an end. This, by the way, this sign right here is called electronegativity. So it's a higher electronegativity on the right than this on the left. There's a higher electron density here than here. Okay? All right. Let's continue. Now let's contrast this with an ionic bond electron cloud. The ionic bond electron cloud, which you recall, looks like this. The electron was completely transferred, like this was for sodium chloride, for example. So chlorine now possesses that electron. Sodium lost that electron. More electron density around the chlorine than the sodium. Okay? Notice no sharing. All right. Let's talk a little bit now about metallic bonds. Now, metallic bonds are formed between atoms which are both on the left side of the periodic table. These are the metals, you recall. And metals are characterized as being malleable, ductile, and lustrous. Think about gold or silver. They can be bent into a shape, they can be pulled into wires, and they're shiny. That's what those three words mean. Now, metals also conduct electricity very well because of the sea of electrons. What do we mean by the sea of electrons? Well, unlike in ionic and certainly in covalent bonding, where the electrons are localized to a particular atom, in metals, the electrons are free to move anywhere. So, for example, in this metal, the positive signs indicate the nuclei of the atoms. The electrons are not confined to the area just outside of the atom, or the nucleus, I should say. They're free to move everywhere, right? They're free to move everywhere. So if you were to imagine, for example, that this diagram right here were a piece of a copper wire, for example, the electrons would be free to move down the copper wire or in any direction across the copper wire because of the sea of electrons. So that's what we mean by the sea of electrons. The electrons are free to move anywhere in the copper wire that they desire. Okay? All right, let's continue. Now, note that the melting points of metals are even higher than the ionic compounds, usually in the thousands, all right? You can melt a metal, but it's usually going to be in the thousands of degrees Celsius. So let's do a little practice now. What type of compound is MgCl2? So let's find magnesium on the periodic table and then chlorine. Notice that magnesium is on the extreme left and chlorine is on the right. So we have a metal with a nonmetal, and when metals and nonmetals combine, we call that ionic. So the first one is going to be ionic. How about CO2, carbon dioxide? Well, carbon is to the right of the zigzag line. Oxygen is also to the right of the zigzag line. When two nonmetals combine, we call that covalent. Now, what type of compound is water? This one's a little bit tricky because of the fact that hydrogen is on the left side of the zigzag line ordinarily. But remember that hydrogen is really in a class by itself. So I want you to know that when hydrogen forms compounds, it forms compounds that are covalent, all right? That are covalent. What type of compound is lithium bromide? Lithium on the left side, bromine on the right side, a metal with a nonmetal? Ionic, all right? Ionic. Okay. Let's take a look at some more bonding practice. The bond above is a nonpolar covalent bond. Notice that there's no pole on one side or the other. There's a perfectly symmetrical distribution of electrons on the left and on the right. This bond between two atoms, this is a bond between two atoms which are identical. For example, chlorine and chlorine, or hydrogen and hydrogen. The type of bonding can also be determined by calculating the difference in electronegativities between these two atoms. For example, fluorine has an electronegativity of 4.0. I'm going to ask that you remember that. And boron has an electronegativity of 2.0. It's much lower and to the left. The difference, of course, between 4.0 and 2.0 is 2.0. Now, since the difference is greater than 1.7, and that's the number that we need to remember, 1.7 is the distinction between a covalent and an ionic bond. So since the number 2.0 is bigger than 1.7, we have an ionic bond when we combine boron and fluorine. Okay? All right. For two identical atoms, the electronegativity difference is, of course, 0. Since the value is less than 0.3, and that's the low end of the scale, so it goes from 0 to 0.3, 0.3 to 1.7, and then 1.7 to 4.0. This is a nonpolar covalent bond that is also known as a pure covalent bond. Okay, a pure covalent bond. That means that the atom or the two atoms are equally sharing electrons. So electronegativity differences between 0.3 and 1.7 are considered polar covalent bonds. All right. So the octet rule, here's what it says. It states that the chemical compounds tend to form so that each atom, by gaining or losing or sharing electrons, has an octet of electrons in its highest occupied energy level. All right, folks, we're going to do the next one in the next video. I'll see you there. Thanks. Bye-bye.